So we're very happy to welcome David Gross today. He's a physicist who's also made substantial contributions to mathematics. He began studying electrical engineering at TU Berlin before switching to physics and writing his diploma thesis under renowned quantum information theorist Jens Eisert at Uni Potsdam. He followed Professor Eisert to Imperial College London, where he earned his PhD in physics in 2008. Over the next few years, he was a postdoc at TU Braunschweig, Leibniz University Hanover, and ETH Zurich. Starting in 2011, he held a tenure-track position at the Institute for Physics at the Albert Ludwig University Freiburg, before accepting a full professor position at the Institute for Theoretical Physics at the University of Cologne in 2015, where he is now. He exploded into the compressed sensing scene with his 2010 paper, Recovering Low-Rank Matrices from Few Coefficients in Any Basis, which introduced the so-called golfing scheme, leveraging dual optimality conditions to prove results for the signal recovery problem. Funny side note, there is a David Gross in the US who worked for the Golf Channel, and if you Google just the wrong way for golfing scheme, you'll get the wrong person. He continued publishing influential papers in compressed sensing and matrix recovery while also doing research in quantum information. The workshop on finite Weil-Heisenberg theory, which he co-organized with Götz Fonder in 2016 as part of the Hausdorff Institute trimester program on the mathematics of signal processing, was the first time that I and other mathematicians had the opportunity to meet certain researchers in quantum information like Marcus Appleby, who spoke a couple weeks ago in this very seminar. We're very excited to have him speak on applications of representation theory to quantum information, and please take it away.
Yep, oh wow, thank you, Emily, for the kind introduction. Let me share my screen here. Okay. Good. Yeah. Thanks for recalling all this ancient history. By the way, when we were working on the golfing scheme, I was also working with Steve Lamia, who's in the call now, and he was probably the first person, certainly the first native speaker of English who saw that term, and he was like, "That's idiotic," something like this. So, all right. So I can't say.
That's not true. I did not say that.
Yeah, that is my phrasing, but I think it was the right meaning. Yeah, there's a second David Gross in the US, who's a Nobel laureate. I get many funny emails. So it's another funny story. Anyway, okay, I want to talk about representation theory of the Clifford group with sundry applications. And I have a bit of a problem. And my problem is that this is a very mixed audience. And so I have no good idea really which language to use, and what is trivial to you and what is very difficult for you. And so I will spend, where's my outline? How can I go to my outline? Aha. So I will spend the first 10-15 minutes of my talk, just like setting the language and recapping things that many people of you might already be well aware of. Yeah, and then I'll talk about the main topic of this presentation. I give many applications, and I have lots of extra slides on actual, even more representation theory than in the beginning. I don't expect that I'll have time to present them, but they're in my deck of cards, and so if you hurry me along, I might be able to talk a bit about it in the end. Okay, so there is this word Clifford in the title of my talk, and the Clifford group is an object that has been rediscovered many times, so it's known under many different names, many different contexts. So in order to find a common language, I will recap the definition, and I will try to take the point of view of time frequency analysis, because I'm under the impression that might match the background of most of the organizers of this workshop. Okay, so 3 slides on time frequency analysis. I start in the continuous variable case, so in the case of functions on the real line or higher dimensional real vector spaces, and I think this might be more familiar to many people. And then the actual talk will be though about the discrete theory. And I just want to set up an analogy. So in time frequency analysis, we work with a vector space. I have some funky functionality here, a vector space of functions, let's say L2 of Rn, so space of functions, taking complex values when evaluated at a point of Rn. And what we will be focusing on are, symmetries that occur in this context. And the most important operations in time frequency analysis are, of course, the time frequency shifts. So if I have some function psi, I can displace it in space, yeah, just by, you know, shifting the argument by some fixed vector q. Yeah, dually I can also displace in the Fourier domain, and so this is the operator here, which acts as a multiplication operator in real space, multiplying with the character, and this corresponds to a shift in frequency space, of course. So these operators here that do these shifts, they have many different names, time frequency shifts. Some people call them Weil operators, and that's probably the word I'll be using most frequently. And they form a group. Yeah, you can combine shifts in position space, shift in frequency space, and if you do it, yeah, so if you shift first by some set of coordinates p prime and q prime, and then by another set of offsets p and q, then the total action will be, you know, a shift. So it's basically a billion. Yeah, so you'll have the total shift here, but it's not quite a billion because there is a phase factor here, and the phase factor depends on what people will recognize to be the symplectic form on R2 of 2 to the n. Yeah, and this non-abelian is of course very important. It's in quantum mechanics, of course, for us it's the origin of the uncertainty principle, and yeah, so it's a very important feature, even though it's just a phase. Good. There is a second symmetry that is going to be important. Namely, we can ask what are the set of unitaries that map these time frequency, that permute these time frequency shifts. Yeah, so I want to have a unitary such that if I conjugate a time frequency shift by that unitary, I get another time frequency shift. And so the kind of permutation that can be realized this way can be constrained because you know, an action by conjugation by unitary must preserve the group law, and the group law depends on the symplectic inner product, and it has kind of like a linear structure. So it's plausible that the permutations that can occur are exactly the linear maps that preserve the symplectic form, and this is indeed true. Yeah, so in addition to these time frequency shifts, we have a representation of the symplectic group acting unitarily on that space of functions. As I said in the beginning, this has been rediscovered many times, so it has many different names. It's called the metaplectic representation in mathematical physics, oscillator representation. I've heard a lot in math. Yeah, the condensed meta people call it Bogoliubov transformations, the bosonic kind, canonic transformations, you know, many different names, all the same objects. So the last object I would like to recall is the complex Gaussian functions. So functions on this vector space, which are exponential, and the exponent depends quadratically on the coordinates. Yeah, and they are very important, of course, in time frequency analysis. I have some like icons here, some pictures of time frequency representations of these Gaussians. Yeah, so-called Wigner functions. We don't need to go into the mathematical definition. Yeah, they're very important here. In particular, they form an orbit under time frequency shifts and Gaussians and symplectic operations that should read. Yeah, so yeah, if you shift in time frequency space, or if you apply one of these Gaussian symplectic operations, then this will map Gaussians to Gaussians. Right, they're very important. For example, in signal analysis, one example are these chirps in one dimension. So these are waveforms where the frequency at any given instant in time depends on the time. So the frequency goes up over time. Yeah, so these signals have many applications. So this is what I do not want to talk about. I wanted to start like this because, you know, in the seminar has harmonic analysis or in the title. So, but what I actually want to talk about is a discrete or finite dimensional analog of all of this. So we will go through again these like 3 different points of view and introduce these 3 different types of objects. And now the vector space of functions is no longer the functions on a continuous vector space, but now it's functions on a discrete set. So let's say ZD, the integers 1 to D with arithmetic modulo D, and then you take n of those. Yeah, if D is a prime, then this defines finite vector space, and let's maybe stick to this case for simplicity. And yeah, so now we have something discrete. If you're a mathematician, you like this. If you more live in MATLAB, maybe this representation as a tensor is more appropriate. Yeah, so a function that takes complex values when evaluated on an n-dimensional vector with entries in ZD. Yeah, this of course can be read as a tensor, yeah, with n indices, each index ranging from 1 to d. And this tensorial point of view is going to be important. Okay, so now we can do the exact same things. We can again define the time frequency shifts using exactly the same way as before, maybe with the most minor modification. Yeah, shift in real space works exactly the same way, just now that the addition here in the argument is no longer addition of real vectors, but addition of like discrete vectors, and we can do the Fourier transformed version, where now in the exponent we have an inner product of integer valued vectors, and it's convenient to normalize in such a way that we take only the result mod d in the exponent. Again, they form a group law that's basically the same as we did before, just now that the phase vector is a symplectic form on this discrete vector space. All right, again, nothing exciting happens here. On the third slide, something exciting happens, because you can again ask the same question as before, what are the unitaries that commute this discrete Weil operators, and you get exactly the same answer. So they form a projective representation of the set of symplectic matrices, but now these are integer valued matrices that preserve the symplectic form on this finite vector space. And now I can introduce the word Clifford group as used in this talk. Namely, it's the group generated by the discrete time frequency shifts and also representations of these discrete symplectic matrices. So that is the group I'm talking about. Right, so there's the final ingredient I haven't yet translated, namely these Gaussian functions. And one can also define Gaussian functions for discrete variables. So I can, take a quadratic form, which is defined by an integer valued matrix, and a character here that is all integral. And I can look at these discrete Gaussians, and one could hope that they are the right finite dimensional generalization of the Gaussian functions that are familiar from time frequency analysis. And they are part of it, but not quite. It turns out that, to get a good theory, you have to look at a few more functions, because these do not actually form an orbit under the Clifford group, unlike is the case in the continuous case. So we have to make it a big bit bigger. And right, and in order to have a more general definition, I will go to a dual point of view and introduce what is known as the stabilizer formalism in quantum physics. This slide is going to be very fast. There's going to be, this definition here has like 5 bullet points, and I will go through them. If you don't understand them, that's fine. For the purpose of this talk, if you just remember this form, you will not miss anything important. Just I want it to be complete for the sake of, well, being complete, I guess. Okay, so here's the construction that people in quantum, work with every day, and the quantum people in the call be my witnesses. Yeah. So so let's start again with this composition law of the time frequency shifts, and so they commute up to this factor, and this factor here vanishes if the symplectic form vanishes. Yeah, and so I can now, using symplectic geometry, describe conditions for Weil operators to commute. And so, okay, so let's make a definition. So a subspace of a symplectic vector space is isotropic if the symplectic form vanishes on that subspace. Yeah, here I wrote R, but I wanted to write ZD. Yeah, but in any case, or maybe I shouldn't have written any field there. This is just a general definition. So if I take an isotropic space and I look at its image under the Weil representation, then this is an abelian group, yeah, because the non-abelian phase here, it vanishes, and such a group is called a stabilizer group. And because these matrices usually commute, they can be jointly diagonalized, and because they can be jointly diagonalized, I can look at their eigenspaces and the joint +1 subspace of such a stabilizer group. This is called the stabilizer code. And if the subspace is not only isotropic, but maximally isotropic, then the stabilizer code is one-dimensional and thus defines up to a phase. It defines a function, and this function is what we call stabilizer states. And now I can connect back to how I started. Namely, it is not difficult to see that two things are true. First, the set of stabilizer states, they form a Clifford orbit. So now we have, we have this orbit that we wanted. And also, secondly, all Gaussians that I introduced before arise this way, but there's a bit more in the set. And so, yeah, if you want to have a closed orbit, then you should start with the stabilizer definition and not with the discrete Gaussians. Anyway, if that was, yeah, I have one more slide on this, namely, right, so now this is a bit unfortunate because so far, I had this like dictionary between continuous and discrete and it worked out perfectly, and now the symmetry got broken. So maybe I have like one kind of like intuitive slide, namely, how are Gaussians related to stabilizer group? Why do I have these two different notions popping up? And the way to think about it is if you take, a Gaussian function on a two-dimensional real vector space, and then you squeeze it. Yeah, so you shrink one axis and you elongate the other axis, and you do it for higher and higher parameter. Then in the limit of infinite squeezing, you will get a distribution that's actually a delta function on a line. Yeah, and this delta function on a line is invariant under translations along this line. And so this is how you can think of these stabilizer states, yeah, as analogs, in fact, of infinitely squeezed Gaussian functions, yeah, which are then characterized by the translational invariance in one direction. Okay, so that's how you can connect these two notions. Right, stabilizer group is the invariant direction of infinitely squeezed Gaussians. And so non-infinitely squeezed Gaussians don't seem to have a discrete analog. Good, right, so yeah, let me sum that up. So stabilizer states were the last piece in the puzzle for our time frequency setup. And yeah, they have many applications. For example, I copied from the website here a piece of the slides of Matthew Fickus in this very seminar, yeah, who was yeah, talking about equiangular tight frames. And you can see, this frame, this analysis matrix he has here. This is actually, the columns are actually stabilizer states. So yeah, they're important in harmonic analysis. They are very important in quantum information theory, where, for example, they form the basis of quantum error correction. So if we ever do succeed in building a fault-tolerant quantum computer, and there's some people in the call who now get paid for doing that at big, companies, big tech companies. So if they ever succeed, they will succeed because of stabilizer codes. Right, so that was my introduction. And now I'm at the point where I can state the central problem that I will be worrying about in this research program, and I will be telling you about in this talk. Okay, and so this problem, I will introduce it from two different points of view, just say the same thing twice because you know it of different languages, and you must understand at least one of the two, or else the remainder of the talk is going to be even more boring than it would have been otherwise. And okay, so here's what I want to do. I want to understand the representation theory of T4 tensor powers, so U mapping to U to the tensor T of Clifford unitaries. And it will prove, indispensable to introduce a graphical notation to take care of, how these different things act. And here's, my first way of introducing it. And it's mainly more, I think it might work better for the physicists and for those who are more acquainted with applied math. My next slide will attempt to do this slightly differently. So I will use these pictures to tell you how things act. So in physics, a vector space is associated with a particle. So for every vector space, in fact, for every CD, I draw a little dot. So every dot is a CD. Yeah. Now, if I draw n dots next to each other, that is CD to the tensor n, which is, as I said before, the same as L2 of ZD to the n. So one horizontal line here that gives you the vector space I was talking about before. So that's the vector space where these, symplectic unitaries act on. But now I don't actually just have them once, but now I look at T copies of these vector spaces, and I will act on every copy with the same unitary. So that's how you should read this diagram. So if that was too vague, let's go and do this like hands down MATLAB style. Here's the representation I want to talk about. So let's walk through these objects once again. Yeah, so we started with the space of functions, complex functions on a discrete vector space, and the elements here are these tensors, psi I1 to In. So if I now have a unitary matrix acting on this vector space, yeah, then the unitary matrix will have, it's a matrix, so which will have two indices, but every index, in fact, has n components, right? Because I'm contracting against these n components. So unitary has, has this shape, you know, if you look at it as a tensor. Right, and now, okay, now fasten seatbelts. Now comes the definition with indices, and then you will appreciate my graphical notation more. You know, so now we want to look at t tensor powers. So that means we look at functions L2 acting on, yeah, a finite vector space, yeah, over ZD, but now the dimension is t times n. So now elements of this vector space, they are tensors, and the tensors have n times t components. Yeah, and I arrange them in a little square like this. So I go up from 1 to n, and I do this t times. Yeah, and yeah, just, you know, this looks like a matrix, and you want to think, yeah, maybe a matrix is a tensor, you know, and I'm talking about two-dimensional tensors, but I'm not doing this. I'm talking about a tensor which has so many indices that the indices themselves are arranged in some tensorial way. Yeah, I'm sorry. And okay, and now I can, you know, I can take a unitary, and I can take t copies of this unitary, and each copy I contract with one row of the tensor. Yeah, so that is the representation I'm talking about. And so here I'm back to my little dots notation, and I hope now you are, you know, you will, you know, be happy with me using this going forward. Good. So now you know what my central problem is. Of course, you have two follow-up questions. You know, why? Yeah. Oh, I see Dustin nodding along, you know. Why? Because I'm broadcasting from Europe. Nobody will beat me out when I say, you know, what the fuck, you know. So I will take that privilege to say that. You know, why would anybody care? And the second question is, like, once, you know, you understand why I care is, you know, what does to understand mean if I want to understand? So these are the two questions I would like to answer next. Yeah. First, why? So I will motivate the why by giving applications, so questions I could answer if I understood this representation theory. Now my problem is that most of the applications I have worked on come from quantum mechanics, and so I try to find like 3 ways of saying things that, you know, work outside of quantum. Let's see whether I've succeeded. All right, and okay, so the first application is to look at orbits of the Clifford group as frames, and to analyze, you know, how dense these frames are in the space of all functions. Yeah, and here's an application, a sample application, which in fact, you know, relates to 2 by now quite old papers already that we've written on this. And so let's consider some randomized algorithm which relies on some IID randomized vector psi. So let me make something concrete. For example, I could be thinking about like a linear measurement in a compressed sensing protocol, you know, where psi describes the measurement, you know, and in reality measurements are deterministic, but I can't prove anything about deterministic measurement matrices. So I randomize things, for example, by choosing each component in some IID way, and then I can prove that recovery will work. Now then I'm unhappy because, you know, I have something in reality which uses a deterministic setup, which I can't prove anything about, but I want to use, and I have something randomized, which I can prove stuff about, but I can't use. And so I want to like narrow the gap. And so I want to engage in a de-randomization procedure. So I want to find, you know, some kind of like less randomness laden protocol that, you know, achieves the same. So one question I could ask, can one replace this IID vector with, for example, a random stabilizer vector, yeah, or maybe a random vector of a random element of an orbit, yeah. So these are very small groups compared to, you know, for example, if I take a Bernoulli vector, you know, there's exponentially many here. There's only polynomially many in the dimension. So, you know, this is much smaller. And, you know, okay, so if I wanted to do this, how can I prove that my randomized algorithm still works? And it's often the case that one can bound the success probability of such randomized algorithms using moment estimates. Yeah, so let's say, yeah, I mean, the success probability depends on the distribution of psi, and I can, you know, like get information about the distribution, for example, by looking at moments. So I take some direction x and I look at the inner product of the random vector in direction x, and I look at the 2t moment, for example, in this direction. Yeah, and then I can rewrite this slightly. I can do a lifting trick, and I can write this, you know, polynomial of order 2t as some linear expression in, you know, the 2t outer product. And then the expectation is over psi, so I can move it into the expectation. And so, you know, these teeth moments or 2t moments, they only depend on the expectation value of, you know, the outer product of the vector to a higher tensor power. And this thing is called the moment operator, MT. And once I understand it, I understand, you know, I understand the distribution of these random vectors. So now if, let's say, if I take like a random stabilizer state, then this moment operator, you know, it will commute with teeth tensor powers of Clifford unitaries. Yeah, why is that? Because, you know, I'm just randomizing over an orbit, you know, and you leave these orbits, its own orbits invariant. So, so I have this commutation relation, and then I can just use, you know, Schur's lemma to describe an operator that commutes with the group action. And this constrains the possible form of the moment operator using representation theoretic data, if I understand it, and often it constrains it basically uniquely. So if you understand the representation theory of u to the tensor t, you can compute moment operators, and then you can de-randomize protocols. Okay.
David, so would you permit a mathematical question here? I just want to make sure I'm following. When you say the representation theory of u, are you meaning like a specific operator, like a Hadamard acting transversely, or do you mean the whole Clifford group acting transversely?
Right. No, here I mean the whole Clifford group.
Okay.
Mm-hmm. Yeah, there's different, you know, different variants of that question, but for now, let's say I want to take the whole Clifford group. Yeah. Okay. So application 2, I have to speed up a bit. I think it's a similar question, but for not, you know, random vectors, but random unitaries. So yeah, so let's say consider again an algorithm that works well, let's say for some generic input. Yeah, but it might work badly for non-generic inputs. For example, you could think of some Johnson-Lindenstrauss type dimension reduction where I take a collection of vectors and I project them onto one fixed subspace. Yeah, then for most random inputs, this will preserve the geometry, but of course there are inputs that lie unfavorably with respect to this fixed projection, you know, so then I will, the Johnson-Lindenstrauss projection will distort the geometry too much. So maybe then in order to get rid of these like special cases that I don't want to treat, I can have like a precondition step where before I apply the algorithm, I map the input to u times the input for some random unitary. Yeah, and now I would like to have a good random unitary. And what does good mean? And here's one like property that these Clifford unitaries have. So they have what is called in quantum information, it's called a gate decomposition. And don't worry if you don't know what that means. It means in particular that every Clifford unitary has a fast matrix vector multiplication, generalizing the fast Fourier transform, which is in fact a special case of that. Yeah. So now we have a big group of matrices that potentially randomizes well, but also has, you know, nice properties because it's structured, for example, fast matrix vector multiplications. Yeah. And so in order to show how good this random Clifford unitary randomizes, you know, again, you can use representation theoretic data in the same way as before. So that's motivation number 2. And motivation number 3 might sound a bit artificial, but let me anyway show it. So here's a question which makes sense mathematically, namely, can one define the Clifford group, or indeed the set of stabilizer states, as the solution set of a bunch of low-order polynomials? Yeah, so I want to have low-order polynomial equations whose solutions are exactly the Clifford group. Yeah, and okay, so why would one care? Let me comment on this later, but let's accept the question for now. So then the Clifford group itself, or the set of stabilizer states, so the variety, they are invariant under the Clifford group, and so the defining equations should inherit the symmetry. Yeah, and again, if I want to find these equations, because order T polynomials, they carry an action of u to the tensor T. If I know the representation theory, probably I can find good equations. And this turns out to be true. And it's in quantum information, it's a slightly less artificial problem. It solves some problem in the theory of quantum property testing. But yeah, I'll touch on this in a minute again. Okay, so now, right. So now we have 3 applications. So I hope not prepared to take on the pain and think about this horrible action a bit. Okay, so right. So now I have to come to my second question, namely, what do I mean by to understand? So what is the goal here actually? And in order to explain this, let me talk about a different action, which is of course a classic object and very well understood already. And this is Schur-Weyl duality, right? And here one starts in a similar setting, but one starts with a much bigger group. Namely, one starts with the full, the full unitary group of the space, not just the symplectic ones. Yeah. So I have the same diagram here. Yeah. Again, I'm looking at these tensor product spaces, but now I take like any unitary and repeat it t times. Yeah. Then one can, then Schur-Weyl duality makes the following statement, which, okay, so the first one is obvious, namely, if you take a permutation in ST, yeah, so a permutation of T objects, then it also acts on this tensor product space by just, permuting tensor factors. So in terms of this diagram, it means I permute rows. Yeah, and then it is true, and this is the first, right? Okay, so then it's true that these 2 actions commute. Yeah, so whether I apply the same unitary on every row and then permute the rows, or whether I first permute the rows and then apply the same unitary everywhere, that's the same. No, that's obvious. Yeah. What is not obvious, but also true, is that these 2 sets, they exhaust each other's commutant. So if an operator A commutes with u tensor T, then it is a linear combinations of permutations. Yeah, so it's the only way you can do it, and also vice versa. If an operator commutes with all the permutations, then it's a linear combination of unitaries. Yeah. So when I say I want to understand this duality, I want to understand the representation theory for the Clifford group, then one meaning I could have is that I would like to understand like a linear basis of the commutant. Yeah, so that is one way of making precise what to understand means. And this is, we have this paper, which I think basically like, for our, like solves this problem as far as we are concerned. This we can completely do. There's a second and more refined notion of what it means to understand the representation theory. And this is to, take the tensor power of these spaces and actually, reduce them out into irreducible representations, each of which are fully understood. And that's a much harder problem. And yeah, we also have, made some progress on this, but, this is far away from being done. And this is what I said in my outline. This is like my final, few slides that I will have no time at all to talk about, but yeah, we are slowly making progress here. But for now, for the rest of the talk, I will focus on this problem and try to understand what is the algebra of operators that commutes with having a Clifford unitary and replicating it t times. Good. And I want to make one comment, namely that Schur-Weyl duality has some fantastic properties, and some of those we will recover. Namely, what is true is that both the algebras that are each other's commutant, they are generated by tensor powers. So for the unitary part, I started with this. I started with taking one unitary and tensoring it t times. Then I found the commutant is the permutation of rows. And now, how can I permute these rows? Yeah, let's say I only have 2 rows, t is 2, and I want to exchange all this Hilbert space with the lower Hilbert space. Then I can do it by first exchanging these two indices, and then these two indices, and then these two indices, and so on. Which means that the permutation also factorizes. Yeah, but it factorizes in some kind of orthogonal way. So this is why you need, in order to talk about it, you need this graphical notation. Otherwise, you would just go completely nuts. Yeah, and this is a very a property that is too good to. I mean, there's no reason to hope for this. Yeah, but it's still true. So that you have these factorizing operators which make things much easier in practice. Yeah, and this means often that the results are independent of n. What do I mean by this? You know, so the commutant here is ST. Yeah, so they are in ST, and this object is independent of the number n of tensor factors I started with. So I started with unitaries on a very high dimensional space, and the dual picture is independent of this big dimension. And that is also a very lucky coincidence that I'll come back to in the applications, yeah, for how this will help us. Yeah, so that we get dimension. It will often lead to dimension independent constructions. Right. Let me skip this. That is about continuous variable. So the question I asked now in the discrete case can also be formulated in the continuous variable case, and there it has been known. In the US, it's associated to the name of Roger Howe, and in Europe, it's associated with Kashiwara and Verne, who Howe found it first, but Kashiwara and Verne actually told people about it, whereas Howe didn't. Okay, but yeah, so the continuous variable version is known. Maybe one word I should say about this. Right. Okay. So yeah, I will skip the lower part, but actually have to talk about the upper part. So okay. So now right. Okay. So let's start. You know, with a situation where these unitaries are arbitrary unitaries. Yeah. Then the commutant is given by permutations. Now I make the primary group smaller. I go from all unitaries just to the Clifford unitaries. Yeah. And because I make this group smaller, the commutant has to become larger. And so I start with the permutations, and now I need to find some superset of the permutations. And I can hope that I'll find a simple superset of the permutations. And one superset of permutations are the orthogonal T by T matrices. No? The orthogonal T by T matrices contain the ST as a subgroup, but they are bigger. And it turns out that this is the right generalization. So whereas if you want to commute with U's with general unitaries, you can only permute your tensor factors. If you want to commute just with Clifford operations, you can rotate them into each other. Yeah, and so this was known before, and since the 1960s in the continuous variable case. And so in a way, you know, what I'm describing next is the realization that this essentially also works for discrete variables. Okay, I actually needed this. Okay, so now enough preparation. Like, I don't know, 40 minutes into the talk, I can actually state the main result. Okay, and so the main result is this.
Question really quick.
Question, yeah. Mm-hmm.
So were you saying that this orthogonal group is the commutant, or I'm not sure if I'm using quite the right word, but replacing the symmetric group in the case when you...
Yeah, that's right, exactly. So it is, I'll give the full statement later in the discrete case where it's a bit more complicated, but basically this. So it is right that the commutant, so the vector space of operators commuting with U to the tensor T for U, these canonical transformations is exactly the linear span of orthogonal operations, which again don't permute tensor factors but rotate them into each other. Mm-hmm. Yeah, I'll give a statement there in a second. Right, okay, so here's the main result. So the main result is this. So the commutant algebra of the Tth tensor powers of the Clifford group over D to the n is generated by Tth tensor powers of, and now we have two types of objects. Namely, it's discrete, so we have discrete orthogonal transformations. So that is the exact analog of the continuous case that was known before. But we have a bit more, namely so-called self-orthogonal CSS code projections. Aha, okay. So now I owe you an explanation of the first bullet point, and I owe you an explanation of the second bullet point. So let's do that in turn. So first, what are these discrete orthogonal transformations? And you know, let's just do it the naive way. Yeah, we can take a t by t integer matrix O, and we say it's orthogonal if you know it satisfies this naive generalization of what it means to be orthogonal mod D. So that's what I mean by orthogonal. And how does it act on this vector space? Yeah, it acts on the vector space basically the same way I just said. You know, not by commuting, but by rotating into each other. So let me make this a bit more precise. So we can give a basis of this two-dimensional tensor space by looking at a delta function. Yeah, at a delta function, and the delta function is now indexed by a matrix F, and the matrix F is the choice of one basis element for each of these n times t systems. So it's a t by n matrix, integer matrix. Yeah, so every t by n integer matrix gives me one basis vector of this tensor space. And then the orthogonal group just acts from the left on this matrix. Yeah, again, if that were permutation, then it would just permute the rows of F, which is what you would expect, but now you know you can rotate them into each other. So these are the discrete orthogonal transformations. Aha, part one, check. Here's an example of a discrete orthogonal transformation. Our favorite examples are what we call the anti-permutations. And an anti-permutation is what you do. You take a permutation matrix, for example, the identity matrix, and then you use the element-wise complement. Yeah. So turn every 1 into a 0 and every 0 into a 1. This turns out to be orthogonal over Z2. So that's what a rotation over Z2 looks like. And okay, so there's some interpretation. Well, let me skip it. So this, yeah, we'll see it again. And so then we have the second kind of object, which are self-orthogonal CSS codes. They are very important in the theory of quantum error correction. And so a CSS code is a particular type of subspace of this two-dimensional tensor, space that I'm talking about. But unfortunately, if I check the time, you know, I should maybe skip the definition, which anyway I only had here to like show the definition. I have no time at this point, you know, to give you a feeling for CSS codes. So yeah, ask me later if you want to know more. But now I can restate the result, and now it makes more sense. So yeah, so in our original scenario, if I take a Clifford operation, I apply it t times, then the commutant is a linear combination of what? You take an orthogonal transformation, a discrete orthogonal transformation, tensor it up n times, or you take a CSS code projection. Yeah, so a projection onto one of these subspaces and tensor it up n times, and these form the basis of the commutant algebra. So it again has this property that the commutant algebra has a factorizing basis. We call this transversal in quantum physics. Yeah, so we start with tensor powers horizontally, and the dual theory is like phrased in terms of, you know, vertical tensor power. So that is very nice. What is not so nice is that this basis here is only partly invertible. Yeah, so these form a group, but these do not form a group, and that has some very interesting properties that again I will lack the time to get into today. Right. Okay. So now you know the main result. Let me now revisit the three applications I told you and like mention how like the theory, you know, can then help to make progress on that. And then I'll conclude. So application one is we wanted to look at application one is actually going to be these polynomial equations. But let's start slowly. So let's say the first realization is that stabilizer states have an additional symmetry. And so how can I construct them? So I take some stabilizer state, so one of these discrete Gaussians, and I tensor it up t times. So before we looked at t tensor powers of unitaries, now I'm looking at t tensor powers of vectors. Yeah? And now this has a certain symmetry, obviously. One symmetry is again the permutations. You know, I can permute this and I get the same object as I did get before. But as a consequence of the theory, you have actually this orthogonal symmetry. Yeah, so you can if you have a discrete Gaussian and a teeth tensor power, then you can have this rotation and it will give you back what you had before. This is very easy to prove, but I don't prove it now. In fact, what I want to show is that, or what I want to claim is here that it's easy to find, a sufficient, to find one of these symmetries that actually singles out exactly the stabilizer states. So here's the statement. So I take an arbitrary psi in this horizontal vector space, and then I take t equal to 6, and I take 6 copies. Yeah, so here is where psi lives, and I take 6 copies. And then I project onto the +1, or that should be a plus. I project onto the +1 eigenspace of the anti-ID. Yeah, the anti-identity here is, again, this funky orthogonal matrix that we had before. Yeah, and this is the projection operator. So if psi is normalized, then this inner product I'm getting here is larger than, is at most 1. And it turns out that it is 1 if and only if psi is a stabilizer. If is clear because the anti-identity leaves stabilizers invariant, but it's also only if. So there's the only way to not get a number smaller than 1 is to take a stabilizer input. And so what we have done now is we have found a set of polynomial equations exactly cutting out discrete Gaussians. Yeah, and it's order 12. Yeah, order 6 in psi and order 6 in the complex conjugate. And one can prove all kinds of optimality statements, and so we have solved one of our problems, namely to find a description of stabilizer states here, but one can play the same trick for Clifford unitaries and to define this group in terms of polynomial equations. Yeah, and in terms of quantum information, one can actually build this anti-identity and can do funky applications with this, but this would take me too far now. Right, application number 2 is finding complex projective designs. And again, I'm referring back to slides and definitions that come from previous iterations. And I think, in fact, the last iteration of this seminar, I think I've seen Caso in the list of participants. So he defined the notion of a spherical T design. So that is a set of vectors, let's say a set of normalized vectors in a complex vector space that whose teeth moment operator, so that is the moment operator that I introduced before, matches the teeth moments of a Haar random state, of a Haar random vector. Yeah, and so if a finite set is a T design where T is big, then it has good randomization properties or good de-randomization properties. And that goes back to the application I started with in my motivation section. So the question is now, so the promise was if we understand the representation theory, we can understand moment operators and what can we do? And there's many results. Here's one result, namely that one can find exact spherical T designs from a dimension independent number of Clifford orbits. Yeah, so ideally, maybe one would like to have just one Clifford orbit, for example, stabilizer states. That doesn't really work anymore if you go to high T, but we can still have, a number of group orbits that only depends on T, but not on the dimension. And the reason we get this is this uniformity property I mentioned before, that the commutant, is given in terms of an object, namely O of T, that does not depend on N, the dimension which dictates the dimension of the horizontal Hilbert space. Right, and then finally let me mention application number 3, which is also like a randomization property, but now we're not talking about vectors, but we are talking about unitaries. Yeah, and so let's start with an old question, namely, we have some group G and some set of generators, G1 to Gk. One can ask how big does M have to be such that the distribution of a random word in these generators approximates the uniform measure on the group. Yeah, it's a very general question with a long history. For example, Percy Diaconus got famous for solving that for card shuffles. And yeah, and now back to this Johnson-Lindenstrauss applications, we would like to have, you know, a simple way of writing good unitary randomizers. So let's make the following ansatz. Let's look at layers and M layers where we alternate between having a random Clifford operation, which we know has nice fast properties. But now the Clifford group, you know, this is, we have to go a bit beyond the Clifford group. So occasionally we'll put a 2x2 unitary acting on just one tensor factor in addition to it, so that we can get out of this finite group. Yeah, and so the question is now, if we iterate random blocks like this, how many do we have to iterate before we get a good approximation to the Haar measure on the full unitary group? And there are applications which I skip. And again, one can, you know, define a notion of design, yeah, in order to quantify how good my convergence is. Namely, I can define a unitary T design to be a finite set, like a measure on the unitary group, such that this integral over, or like maybe it's a sum over a finite set, is the same as the full Haar integral up to Tth order. Yeah, and then I can also make it epsilon approximate in some norm, but let's skip the details. And right, and here is again another result using this duality theory. Yeah, which the paper is here, and we showed that if you have a number of non-Clifford gates, so the number, so M, the number of iterations, the number of non-Clifford gates, that scales as t to the 4 and log 1 over the approximation, then you get like an epsilon approximate unitary T design. And again, the thing to notice is that it's dimension independent again. Yeah, so the density of non-Clifford goes to 0 as n goes to infinity. Yeah, and so that's why we called it quantum homeopathy and thought it was funny, and we got a big discussion on the internet whether or not that was funny. But again, we have this dimension-independent construction, which maybe is surprising, certainly surprised us. And the root of this dimension-independent construction is that the commutant O of t does not depend on the dimension of the horizontal Hilbert space. Yeah, so a homeopathic dose is enough of non-Clifford ingredients. Good, and then I'm done. All right, so summary. We found the commutant. I didn't explain this. I simplified things a bit in my talk, so I didn't explain what that means. So discrete orthogonal transformations and CSS code projections, and there's many applications, of which I mentioned the few which I could like maybe indicate without, you know, having to teach you quantum mechanics. And then there is this entire further deck of slides with my favorite representation theory that I have absolutely no way of talking about because, you know, that's just ridiculous. And I skip forward, even though it's very nice theory, to the thank you slide. So thank you.
So thank